Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video. All math-based, of course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step one aside as we jump into section 10.2 in the Big Ideas Math Integrated Math 2 textbook on finding arc measures. Last time we looked at some circles on how segments intersect, whether it's chords, tangent lines, secant lines, a lot of things on tangents really, and let's not forget what those things are, but this is going to go in a little different area. We're going to talk about, I believe, I haven't really looked at it, but I don't think we're finding the lengths of arcs, but measures, yeah, arc measures. So arc measures, central angles, I think will come into play. I don't know what else, but I'm excited to look. We're going to start with the lecture portion, and if you want to check out the description section below, you'll find a PDF of this textbook section, as well as we're going to go to the problem set. So check out the timestamps and find out when I'm going to go ahead and start that. If you want to skip this lecture portion outright, I'll try and go as fast as time permits. So without further ado, guys, let's go ahead and take a look at what's going on here. A lot of vocab, once again, and a lot of them are kind of within the same realm of things. It's going to be very fast to pick them up if you're ingrained. Central angle, minor arc, major arc, semicircle, all three of these run in tandem together. Measure of a minor arc, measure of a major arc. Okay, so, right, there's not too much. Adjacent arcs, just like adjacent angles that are next to each other. Congruent circles, all right, so a lot of things with arcs, basically. And the word central angle. So that's the big thing, arcs and central angles. We're going to find arc measures, identify congruent arcs, and prove circles are similar. Ooh, we're going to do proofs. Okay, so we have to... I didn't even know that was a thing, proving circles are similar. I'm legit. I didn't... Obviously, anything's the same, but why multiple? Okay, all right, let's go. Finding arc measures. A central angle of a circle is an angle whose vertex is the center of the circle. In the diagram, angle ACB is a central angle of circle C. So take a look right here, guys. We're going to be doing a lot more with these, I'm sure, in the future. Oh, I know. We're going to be doing a lot more things with central angles right here. This is a central angle right there. This ACB. Boom. C is your center. We make an angle out of it. Perfect name, central angle. If measure of angle ACB is less than 180 degrees, then the points on circle C that lie in the interior of angle ACB form a minor arc with endpoints A and B. Okay, so let's start talking about arcs. Now, remember, the circle is not everything on the inside. The center is not part of the circle. It's a feature that describes the circle. It's not one of its points. The points on the circle are these ones right here. Boom, 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 boom. Okay, that's the circle. So when they say the points on circle C, they're talking about these points right here. The points that are in the interior of the angle on this circle form a minor arc right there, that A to B. They say if the angle is less than 180 degrees, then a minor arc is formed. So this is less than 180, and here's your minor arc on the circle with that. Now, they're going to talk more about the measures in a moment. I'll go ahead and let them speak on it. I just want to make sure you understood what they're saying. Excuse me. The points on circle C that do not lie on the minor arc form a major arc with endpoints A and B. So minor arcs are arc measures formed from central angles that are less than 180 degrees. They just implied the next part. Major arcs are arcs that are more than 180 degrees. If it's everything that's not the minor, then it's the major. They didn't yet mention how to name them. Again, I'll let them do that. A semicircle is an arc with endpoints that are the endpoints of a diameter. And again, kind of implied here, a diameter like this, boom, a diameter has a central angle of 180 degrees. So a central angle that's less than, you might not see it as an angle, but it is. So an angle that's less than 180 degrees has a minor arc. We're not really talking about this angle per se, but outside of the minor arc would be the major arc, which means we're talking about something more than 180 degrees. And at 180 degrees, you have a semicircle right there. And I think if I said the word semicircle, anyone here without hearing my knowledge would know what we're talking about, half of a circle. Okay, minor arcs are named by their endpoints. Perfect. The minor arc associated with angle ACB is named arc AB. Take a look at it. It's like a segment bar, but it's an arc bar, if you will. It kind of loops like that. So they call this arc AB. Use two letters, the endpoints. Major arcs and semicircles are named by their endpoints and a point on the arc. The major arc associated with angle ACB can be named arc ADB. So you use two letters to do the minor arc, so we know exactly, we're not going from A to B here, we're going from A to B there, but if we want to go this way, we have to include a third letter, which means we have to include another point that's on it. They will be nice enough to give you another point to talk about it if we're going to. So here's another point D that's not doing anything else other than saying, hey, it's a point that's on the circle. that I can now name A, D, B. Notice D has to be the middle letter. A and B have to be endpoints. You could also say arc BDA. But using 3 letters would be major arc. Now a semicircle. Let's say we had a semicircle like this right here, and this is a point A, right? Let's call this point E, I suppose. We could call this arc BAE. That semicircle, excuse me. We call the semicircle BAE. We could call this semicircle EDB. Why, Mr. Robinson, why can't we just call it EB? Because then we don't know which way we're talking about. Thankfully, they have the same measure, but we want to indicate a certain version, so we would use 3 letters for that. Again, I'll let them do that as a whole. Okay, so they talk about measure of minor arcs. Measure of minor arcs less than 180. Measure of a major arc is greater than 180. That's a study tip as we start talking about measuring arcs. The measure of a minor arc is the measure of its central angle. If the central angle is 50 degrees, the minor arc's measure is also 50 degrees. We have to be very specific to include the units for degrees here. It's not a length we're referring to when we talk about its measure. There is a length of the arc. That's not what this section's about. It's about its measure. The expression measure of arc AB, MAB can be read as the measure of arc AB. The measure of the entire circle is 360 degrees. Yes, as we go around this circle, it's a whole 360. As we navigate the central angles and you rotate your body a full 360, that's what we're talking about there. The measure of a major arc is the difference of 360 and the measure of the related minor arc. The measure of a semicircle is 180 degrees. So I mentioned that one before. Now they bring it up. So the measure of the minor arc, ADB, this guy right here, I should really use different colors. If this guy's 50 and the whole thing's 360, you can do 360 minus 50 and you get 310 degrees for the measure of arc ADB, the entire thing. And I think that makes sense to you guys. They all kind of build off that way. So let's look at some examples. Example 1, finding measures of arcs. Find the measure of each arc of circle P where RT is a diameter. So they tell you that, but it is a chord that goes through the center. So I think we can make that assumption. Anything else that we see looks like a radius. So these are central angles. Now, they ask for the measure of arc RS. Oh, these are ones they do. They ask for the measure of arc RS because the central angle is 110 degrees. They call it an intercepted arc. I'm saying that phrase. Did they use that as a... I don't want to say that just yet then. Okay, the arc measure, I'm going to accidentally say that a lot. The intercepted arc, I just said it, of the central angle is also 110. Boom, 110 degrees. RTS is a major arc. Here, they want measure of arc RTS, this guy. This is everything that's not the 110 out of 360. So we'll do 360 minus 110. That's where we get 250. And then RT is a diameter. So RST is a semicircle. Because they're asking for the measure of arc RST, this will be 180 degrees. They didn't ask for this one, the measure of arc TS. But this is the difference of the 180 and 110. That would be 70 degrees, for example. 70 degree central angle, 70 degree intercepted arc. I just said it. All right, 2 arcs of the same circle are adjacent arcs when they intersect at exactly 1 point. You can add the measures of 2 adjacent arcs. The arc addition postulate. It's like the segment addition postulate, angle addition postulate. As long as they join up together, we can add them together and we get the whole thing. The measure of an arc formed by 2 adjacent arcs is the sum of the measures of the 2 arcs. If I add this arc measure with this arc measure, I get the measure of that entire thing. That's what they're saying there. Measure of this major arc ABC is the measure of arc AB plus measure of arc BC. Boom plus boom equals boom. Cool. How are we going to use that? Let's find the measure of each arc here. We want to find the measure of arc GE. Well, to find the measure of arc GE, you can apply the central angles. Literally, you can either add the central angles and apply that as its intercepted arc, or you can come up with what these two things are and add them together, which is what they do. 40 plus 80 is 120. GE's arc is 120 degrees. Measure of arc GEF. Now, GEF is this entire set right here. You take the 120 that we just got plus an additional 110, you get 230 degrees. And measure of arc GF is everything that's not measure of arc GEF. So subtract the 230 from 360, and you get 130 degrees on that one. So that's the 130 plus everything else that you saw. Okay, another example, finding measures of arcs. A recent survey asked teenagers whether they would rather meet a famous musician, athlete, actor, inventor, or other person. I wonder what I would do. Growing up, I would have definitely said athlete. Absolutely. Let me move myself. I would have absolutely said athlete. Now that I'm 35 years old, I'm besting the ages of all the other ones and stuff. Can't say I'm better than them. I'm thinking about this too long. I would probably do certain actors. Depends on the actor. I'm not really big on inventors unless they're a classic. Oh, I want to meet Edison or whatever. I'd do an actor, Christian Bale, something like that. All right, anyway, the circle graph shows the results. Find the indicated arc measures. So these degrees They're not percentages, but these degrees are represented, I guess, with the angles. Measure of arc AC is the sum of this AB plus BC, and I call them as such because they're minor arcs. So 29 plus 108, we get the 137 degrees. It's measure of arc AC. I don't really know what the word problem has to do with this stuff, but whatever. Measure of arc ACD, where's that, ACD? ACD is this whole thing. It's got to touch C to get to D from A right there. So we're going to take that 137 and add an additional 83, so we get 220. Measure of arc ADC, so this one goes right here. ADC is now this guy. 79 plus 61 plus 83, I'll let that calculate. Oh, you can also subtract measure of arc AC, which we found, right? More than one way to do it. If we already found this to be 137, we can subtract 137 from 360. And then lastly here, measure of arc EBD. EBD is this whole guy. It's just subtract 61 from 360 instead of adding all those ones up. And you do that, you get 199 degrees. Okay, so monitoring progress, we'll leave it be. I'm spending a long time talking about kind of the same thing. Hopefully this sounds okay to you. Literally, we're just adding numbers right now. All right, identifying congruent arcs. Two circles are congruent circles if and only if a rigid motion or a composition of rigid motions maps one circle onto the other. Sounds like transformations. Do a translation here. You can't really reflect or rotate circles, but if you just translate, just bring it on over. This statement is equivalent to the congruent circles theorem below. Two circles are congruent circles if and only if they have the same radius. Well, yeah, that makes sense to me. Same size radius, same circle. And they say if and only if. So they're congruent if they have the same radius, and they have the same radius if they're congruent. Now, what do they want to do with those examples? I don't really know. Looks like either we have to do a proof or they'll show us one later. Two arcs are congruent arcs if and only if they have the same measure and they are arcs of the same circle or of congruent circles. So I have a congruent arc BC and DE because they could have the same measure and arcs of the same circle. Okay, so congruent central angles theorem. In the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding central angles are congruent. So yeah, if this angle is congruent to this angle here, their arcs are congruent. And I don't really know what the theorem means beyond, like, I think we know that, but I don't know what it's going to use an example that we're like, oh, we didn't understand that before. So we'll find out how they want to use that for sure. That's totally okay. Identifying congruent arcs. Let's tell whether the red arcs are congruent. Explain why. I guess here's an example. Explain why or why not. Well, these arcs should be congruent to each other, C, D, and E, F, because they share the same central angle, right? By that theorem. That's kind of what they're saying down here. Therefore, they are. The next one right here. Oh, okay, because the circles can be different sizes. I got it. So I have concentric circles right here. Circle Q. I guess they're both forms of circle Q. Same center. But here's an arc RS and here's an arc TU. Remember, it's not length, it's measure. They're both 90-degree arc measures. So they have the same measure. Oh, they said whether the arcs are congruent. Oh, got it. They have to be of congruent circles. I see what they're saying. Okay. They have the same measure, but they're not congruent arcs. And that, actually, I should have known that. That makes sense to me, because you're not mapping one onto the other. So they have to be congruent circles as well. They are not, therefore the arcs are not. Got it. Okay, these circles, I don't know how you can tell the circle. Oh, with the radii, you can tell the circles are congruent. So here, it's the same circle. Now I get what they're saying. Here they have the same circle, therefore the arc measures being the same means the arcs are congruent. Here we have congruent circles because the radii are congruent, and with the same arc measure, that means these arcs are congruent. The same central angle measure, that means the arcs are congruent as well. Okay, so cool. That's that moving forward. All right, let's skip past that. Similar circles theorem. All circles are similar. It's a great theorem. I agree with it. You can grow and shrink them in a certain amount, right? None become oval or anything like that. You can apply dilations, which I guess is what they're asking us to do. They said apply transformations. Given circle C with center C and radius R, given circle D with center D and radius S. This is a proof. I hope it's the only time we have to look at the proof. Prove that circle DC is similar to circle D. I think you're going to map one onto the other. Okay, translate it. So it maps point C onto D. So same center. Boom. Put right next to each other. The image of C is circle C prime with center D. It's right here. So the concentric circles now. Now we're going to apply a scale factor to this. Circle C is a radius of r, circle D is a radius of s. So if you divide s by r, that's what you have to multiply by to enlarge it. The dilation maps the set of all points that are r units from point D to the set of all points that are s units from point D. So it's going to bring them up bigger, so now there's perfect overlap right here. Circle D is the set of all points that are s units from D, so the dilation maps C prime to D. Circle C prime to circle D. Two arcs are similar arcs if and only if they have the same measure. All congruent arcs are similar, but not all similar arcs are congruent. Similar, that's not the water I want to use. Two arcs are similar. Yes, so this one before, these arcs were not congruent. They were only similar. They're both 90-degree measures. It didn't mean they were congruent. You could grow one into the other. They are similar. These ones were congruent, I guess, and similar. Congruent and similar, but just similar, not congruent right there. Let's see what they were saying beyond that. For instance, example 4, maybe this is the example I was just talking about. The pairs of arcs in A, B, and C are similar, but only the pairs. Yeah, that was the one I just pointed out before. Perfect. Okay, is that it? Oh, perfect. Nice. All right, so I don't know what we're going to do with those problems. I guess they're going to ask us, and we'll see. All right, let's start the vocabulary and core concept check, then we'll do the problem set. I think that example set, I'm going longer on lectures. And probably because I paused talking about actors and athletes and stuff like that, but I'm going longer in lectures, and I really like to narrow that down. All right, vocab. Excuse me, copy and complete. If angle ACB and angle DCE are congruent central angles of circle C, then arc AB and arc DE are blank. It would help if you kind of saw a drawing and understood it. I think you might know the answer either way, but let's take a look. So I have central angles here. Let's just say boom, and let's go boom, like that. So we have ACB, looks like circle C, ACB and DCE. We are congruent central angles here, boom and boom. So they're congruent. They're saying arc AB, that's this minor arc here, and arc DE, this minor arc here. What's true about them? They're also congruent. They're from the same circle. They have the same central angle measure. Therefore, they are both congruent. That's what we're doing there. All right, which one doesn't belong? Which circle does not belong with the other three? Explain your reasoning. I have a 6-inch radius guy here, 1 foot diameter here, a 12-inch radius here, and a 6-inch diameter here. Looks like that 3 of these things are 1 foot diameters each, or 6-inch radius. This is literally 6-inch radius. 1 foot is 12 inches, which means this is a 6-inch radius right here. 12 inches, 6-inch radius right here, and this is a 6-inch diameter, which is a 3-inch radius. So these are all A's, if you will, whereas this one is a B. Explain your reasoning. 3 of them have a radius of 6 inches, so they are congruent circles. So the first 3 are congruent circles with radius of 6 inches, whereas the other, the last one is not. Okay, the last one is a radius of 3 inches, so there's the idea. All right, guys, we're going to go ahead and get started with the rest of the problem set. I believe it's numbers 3 through 38. Let me pause for a second anyway. I want to get the other text box thing open that goes right there. Give me 1 sec. Okay, I think I got it up. Okay, so let's get started. Here we go. All right, we're going to start with numbers 3 through 6. Name the red minor arc and find its measure, then name the blue major arc and find its measure. So I'll keep the drawing as it is, and I'll go ahead and get started on this side here. So number 3, with that drawing, the red minor arc we will call arc AB. Minor arcs are going to be, they're going to have two letters. So I'll just put it like that, and I'll say measure of arc AB equals. I hope that's okay. That red's a little bouncy, though. I'm going to go ahead and stick with, I'll make it red. Do you want me to? I'll make it red, but I'll just have it as that color, if that's okay. Okay, measure of arc AB is 135 degrees because its central angle is 135 degrees. Now, the major arc is in blue. We're going to use 3 letters. We go from A through D to B. So we'll call it arc A, D, B. Now, when I say measure of, that's just that part. Here's the name. Now we'll say measure of. Measure of arc ADB, we got to take 360 and subtract 135. It's everything that's not the 135, and that'll be 225 degrees. Remember, we will have degrees with all these answers here. So boom and boom. Okay, that's number 3. Number 4. Now, all these are the same process, exact same process for each one. Minor arc will be something less than 180. Major arc will be something more than 180. Do the subtraction from 360. So hopefully this will make a lot of sense. So here's arc EF, that red one, that's the minor one. And the measure of arc EF is 68 degrees because the central angle is 68 degrees. And then the blue major arc, we can call we can call arc EGF, and let's find its measure by doing 360 minus 68, which is 292 degrees, like so. I don't remember what I was going to say. Oh, you can reverse the lettering. I could call it FGE as well. I'll probably either go alphabetical or just starting from a letter, and I'm not going to think too hard on it. Hope that's okay. Number 5, we can call that arc JL. Arc JL, we're going to find its measure as 120 degrees, that central angle. I think this is all they're asking me to do. There's not much beyond that. And then the other one, we can say JKL. JKL is the measure of the major arc, and its measure is going to be 360 minus 120, which is 240 degrees. And then the last one, the minor arc is the one in red, and you can tell because its central angle is 170 degrees. And if you go by scale, you can see that it bends a little bit concave and inward. So we do call it arc MN. From M to N, we go in this direction. Hold on. We go in this direction right here. The minor arc, not this direction here. That's a major arc. So the measure of arc MN, that's a lowercase m right there, is 170 degrees. And then the measure of arc, the other one's MPN, and yes, you do have to use that letter in the middle. Measure of arc MPN is 360 minus 170, which is 190 degrees. So each one had the same exact process, subtracting from 360 to find the major arc, and that's the one that they define. It doesn't look like they'll name convex angles for us, and I wouldn't expect them to. All right, numbers 7 through 14. Maybe these ones go really fast, and I don't know, maybe we can just copy and paste that whole docket. I'm not sure. Probably stick with one black color this time, though. Number 7 through 14, identify the given arc as a major arc, minor arc, or semicircle, then find the measure of the arcs. So arc BC, I don't have to look at the diagram. If they use 2 letters, it's a minor arc. So arc BC is a minor arc. The measure of arc BC, I do have to look at the diagram. So arc BC is based off its central angle of 70 degrees. Measure of arc BC will be 70 degrees, just like so. So number 8, measure of arc DC, also 2 letters, that'll be a minor arc. Measure of arc DC is a minor arc. I want to try and do something. Give me 1 second. This will be a little weird. I'm going to write the words major arc, minor arc, and semicircle. I don't think you can see what I'm going to do next here. I'm going to try and select these options and do what's called an infinite cloner. Oh, shoot. These ended up being 2 different. Oh, man. I tried to give it enough time so that these were 2 separate writing things. I hate when they group them together like that. I know I'm spending more time on this than I need to. Let me try that one more time. Minor arc. I'll give it time. And then I want to write semicircle. Okay. So I made an infinite cloner on that one. Let's do an infinite cloner here and infinite cloner here. Okay, so here's what's going to happen now. Every time I write that, I can drag these in. Boom, and boom, and boom, and boom, just like that. So I don't have to keep writing it over and over. Clearly, I could also type it, but that's too much for me as well. All right, minor arc for DC. Its measure, the measure of arc DC looks like it'll be 65 degrees because its central angle is 65 degrees. All right, number 9. Let's do the measure of arc ED. 2 letters is also going to be a minor arc. Again, I'm not looking at the figure. It has to be that, literally. There's no other thing it could be. So ED is a, wait for it, minor arc. That saved a lot of time. It's a few problems, actually, so I think it did save a little bit of time. Measure of arc ED is going to be 45 degrees. So we've seen a 70, 65, and 45 degrees. These arcs, by the way, were all adjacent. So I don't know if that's going to show up later when we do something with it. And number 10 is also a minor arc. I don't think we're doing any more minor arcs after this one. So number 10, AE. Now here's the problem. Those things are going to go out of the picture, and I can't get them anymore. So AE, also a minor arc. It probably would have been just as easy to copy and paste, but minor arc right there. measure of arc AE is 70 degrees. So that's what we're doing with those, just identifying them, and boom, we got them. All right, the next four are either major arcs or semicircles, and you can just tell because, let me bring these down. We know they won't be minor arcs anymore. Either major arcs and semicircles, and you can just tell because they have 3 letters. Now, it's only a semicircle if it's made from a 180-degree angle measure. Either we can add those, or made from a diameter. A diameter is a chord that goes through the center. So let's look at number 11. Let's look at arc EAB. EAB. I feel like I should be pointing the arrow the other way, but that's okay. EAB starts from E, goes through A, ends at B. From E to B in this direction, this chord right here is also a diameter. Or if you add, well, I guess that's the next answer. But that is a semicircle. That's a semicircle. So not a major arc. The measure of arc EAB, just like any semicircle, is 180 degrees. Whether you're adding the 70 and 110, which I'll do in this case, to get that, or just understanding that all semicircles are 180 degrees is your call. Clearly, that's what that central angle is supposed to be if that's your diameter. Number 12, arc ABC. Arc ABC. ABC. From A to B to C is also another semicircle. Maybe the last two are major arcs then. A to B to C is also another semicircle. A to C is a diameter. So this is, just like the last one, a semicircle. I thought these questions would go faster. And measure of arc ABC is therefore 180 degrees. No work really needed on that. 2 more. Number 13. I'm going to guess major arc without knowing what it is. Measure of arc BAC. This time, letter order again matters. You could do CAB or BAC, but notice that A is the middle letter. Therefore, we start at this one, go around and end at this one. That's truly a major arc there. So arc BAC is a major arc. Let's drag that one down. And the measure of arc BAC, you have different ways you can do this. You can add up all these other measures here and, whatever, but it's also 360 minus the 70, right? Any major arc, you just subtract the minor arc that it comes out of. So 360 minus 70, which is 290 degrees. And then number 14, as I kind of run out of space here, number 14, we need the measure of arc EBD, and EBD itself, by the way, is a what? EBD. I'm not going to mark it up. I'm just going to point to it. So E through B to D, it's everything but just the ED, right? It's clearly a major arc. And we're going to do 360 minus 45 to figure that one out. So that's going to be 315 degrees. Measure of arc EBD is 360 minus 45, which is 315 degrees. Awesome. Okay. So that's up through number 14. Let's keep moving forward. Numbers 15 and 16 find the measure of each arc. So now it's a single problem with 4 different parts. How nice of them. JL, you know what I'm going to do here? I am going to copy and paste this one just because I can. I'll copy and paste both of them. Get them ready to go. They always say copy the diagram, don't they? Not this time, but copy the diagram. Literally copy the diagram. Looking good. There we go. All right, so number 15, I don't know why I moved this. Number 15 is here, and number 16 is there. There we go. Pretty nice. Okay, what do they say? Find the measure of each arc. JL. JL's arc, the minor arc right here, we have to add 53 and 79. They're adjacent arcs, and we get that. We get 132 degrees. Boom. Boom. Measure of arc KM. KM is this minor arc right here. We go across the shorter way. We do 79 plus 68. So that's going to be 147 degrees. Maybe this is why I shouldn't have copied and pasted. JLM. J through L to M. The fact that they used 3 letters meant it was either semicircle or major arc. Now we add all 3 of these together. So JLM is going to be 53 plus 79 plus 68. I know 53 plus 79 is 132. 132 plus 68 is 200. 200 degrees. It looks like more than 180, and it's supposed to be more than 180 as a major arc. And JM is a minor arc. JM is everything that's not the 200 degrees from the 360, so that'll be 360 minus 200. So you can use previous answers to get other ones. Clearly, I'm kind of doing a bit of that. I even did it on this problem without showing you. All right, number 16, find the measure of each arc. Now, they're getting you a little, it's a little tricky here. Not tricky, but, you have to go off the properties that you see. First, they ask for RS, right here, RS. Now, there's nothing marked there, but QS is a diameter. Therefore, QRS is a semicircle. So for RS, we take 180 and subtract the 42 that's here. Anything that's not 42 from the 180 is this guy right there, which is 138 degrees. I'll use blue on some of these ones to not get too colorblind with them. QRS, it's interesting that they have that one next and didn't kind of have that one first, right? QRS is that semicircle I literally just had. So QRS is 180 degrees. I would have rather had them kind of start with that one. QST takes that semicircle plus this additional amount. Now, what's this? Here's the cool part. Vertical angles are congruent. Boom, boom. Therefore, this is 42, so is that. So this is 180 plus 42 degrees right there. 180 degrees plus 42 degrees, which is 222 degrees. And a cool answer. And then QT is the minor arc on this other side here. QT is the minor arc that's not the 222 degrees there. So we take 360 minus 222, and we get a number I got to think about. 138 degrees. Okay. So there are those two. Sorry I didn't bring this down. It's just because I had the problems already written up here, and I was like, all right, let's go into it. All right, number 17, let's model with mathematics. We kind of had an example one like this that the poll doesn't mean much, the survey. Just uses degrees, and we move on from there. All right, number 17. I was about to write 17 degrees. A recent survey asked high school students their favorite type of music. The results are shown in the circle graph. None of this looks right. What's the other? 47, I thought this was percent. 47 degrees of them are not going to say rock. Everyone likes hip hop and pop. Oh, everyone likes pop, dude. I hate pop. I hate that my rock stuff is pop now. Country, R&B, let's go. I'm a rock guy. All right. Anyway, find each indicated arc measure. The measure of arc A. Literally, they're doing nothing on the word problem with this stuff. And any charts, they would use percentages. So I just think it's kind of a weird problem. I'm just going to say that. Anyway, measure of arc AE. Like, why do they bring it up? Measure of arc AE. From A to E, we go the minor route, and we're going to be adding some values up. We have 17, 26. I almost want to use a calculator here. 28 and 32. So all four of those, this is what I can at least say out loud. We're adding all of R&B, hip-hop, rap, folk, and Christian folk as we find their degrees. Remember, it's not a percent. We do degrees. So this is 43, and then 71, and then 103. I apologize if I get anything wrong in my calculation. You can, of course, try it for yourself. This video is just a guide. It is not an end-all, be-all. That being said, the calculation, the inputs proper was the output, right? I think so. All right, measure of ACE, A-C-E. From A through C to E, it's everything that's not this. So my answer is going to depend on my previous answer. If my previous answer was wrong, then this answer will be wrong as well. But 360 minus 103 is 257 degrees. 257 degrees. So take all the 360 and subtract what wasn't in part A. Part C, measure of arc GDC. GDC. Let's erase what was there before. G, where's D and C? So we got to go the major direction, obviously through D there. 28, 32, 47, 89, hut, hike. Let's add all those up together. 28. And if I have a faster way to do it, I'll tell you about it. I can't think of what might have been faster here. I don't know. 20 plus 32 is 60, plus 47 is 107, plus 89 is 196. 196 degrees. Part D, they want the measure of arc BHC. This is all one problem. I wish they were different problems. BHC this is the big one, goes around like this. It's everything but the 55-degree arc, measure of country. Everything but country. So 360 minus 55, and let's get 305 degrees on that one. Part E, measure of arc FD, that is a minor arc. From F to D, and it also hits that E, so we're going to do 32 plus 47. 32 plus 47, we get 79 degrees from that. And the last one, F, measure of arc FBD. I don't think we have any semicircles here. FBD, it's everything that's not the Christian and rock group that we're from this last sum right here. So I can do 360 minus 79 and save myself some time. And I will get 281 degrees. Okay. All right, that's number 17 on modeling with mathematics. Let's go to 18 on abstract reasoning. It's another survey. I don't know what we're going to do with it because we're not modeling with mathematics. Now we're abstract reasoning. The circle graph shows the percentages. Shows the percentages of students enrolled in fall sports at a high school. Is it possible to find the measure of each minor arc? If so, find the measure of the arc for each category shown. If not, explain why it's not possible. So it is possible. Taking a percentage of something means you multiply, well, a lot of different ways you can say it, but there's a decimal equivalent to a value. 15% is 15 out of 100, which means 0.15, things like that. They want us to find the measure of each, so we're going to do that. So you multiply that percentage decimal equivalent of like 0.15, etc. We multiply it by 360. 15% is 15% of the whole. The whole is 360 degrees, and that's the measure that we'll get for all of them. So let me first type out. I'll probably type this whole thing. So I'll say you can. Now I was thinking we were going to do the other way before, but you can find the measure of each arc from percentages by taking the percentage of each fall sport out of 360 degrees. Percentage out of 360 degrees, find those values there. Now, taking a percentage is a mathematical thing that we're going to be doing, so let's take a look at what that looks like. Let's start with the... I said I was going to type this all. Let's try and keep going with that. Let's have the high school balls. Football, foosball. Football, soccer, volleyball. Oh, I thought this would all fit on the right lines here. Cross country, and none. So for football, I'm trying to tab over. I guess I can't. For football, we're going to take 20%, multiply 0.2 times 360, which is 72 degrees. And then soccer, we're going to take 30% of 360, 0.3 times 360, which is 108 degrees. Wait. Is that right? I think so. Which is 108 degrees. Volleyball, we're going to take 15% of 360, which is 48. Wait. No, I'm sorry, 54. Oh, it's half of 30%. Duh, I should have done that. 54 degrees. Cross country, 20% of 360, also 72. Now, by the way, all these should add up to 360 in the end, right? Because these should add to 100%, and these should all add 360 degrees. None is 15% of 360 as well, which is also 54 degrees. So 54 plus 72 plus 54 is 108 plus 72, I suppose, is going to be 360. I'm going to go ahead and do that. Is that all they asked? Is it possible to find? If so, find the measure of not. Okay. All right. Got it. Okay. In exercises 19 to 22, tell whether... Sorry, I was going to see something really fast. I wanted to know if they had any vertical angles. I guess not. In exercises 19 to 22, tell whether the red arcs are congruent. Explain why or why not. So the idea behind these ones, y'all, is if they exist in the same circle with congruent central angles, then they are congruent arcs. So that's what number 19 is all about. If you'll allow me, I'm going to just measure. I'm going to do some things over here. Well, actually, I'll write them over here. I want to find the measure of angle. Well, they don't give me a middle center point, so I guess I won't do that. Should I copy and paste? No, I'm not going to. So arc AB is 70 degrees right here. I need to see if arc CD is also 70 degrees. What I can do is subtract all of the, well, I can add all these up and subtract from 360. So I want to find out if the measure of arc CD is going to be 70 degrees as well. So 360 minus 180. I guess I only need 360 for everything. I could have just done 180. So let me try that again. 180 minus, because it's a whole semicircle, right? 180 minus 70 plus 40, which is 180 minus 110, which is 70 degrees. So because this one's also 70 degrees as well, and they exist in the same circle, then yes, these arcs are congruent. So yes, arc AB is congruent to arc CD. Sorry for taking so long. I'm thinking logistically on how I should come up with how to say these things. Number 20, here's the thing. Even though they share the same central angle of 85 degrees and they have the same measure of 85 degrees, they say explain why or why not. I didn't really do this here. Same circle and arc measure. This one has different circles of different sizes. Even though they have the same arc measure, they're not congruent. So not congruent because different size circles. Differently sized circles, whatever. Differently sized circles with same angle measure. With same arc measure. All right, number 21. Number 21 is the same circle. What are they asking us? Tell whether the red arcs are congruent. Oh, I didn't see those two different problems, or two different circles. So this one here, they show a radius of 8, and in this one they show a diameter of 16. That means that this radius is congruent to this radius because they're both actually 8 here, right? And I guess this would be 8 as well. Sorry, they marked that there. Now, they have a 92-degree central angle. Therefore, with congruent circles, we can say that these two arcs, VW, is congruent to XY because congruent circles, I don't want to do that. Not congruent. So congruent circles with same arc measure. And number 22, we have a diameter of 10 and a diameter of 12. Both are semicircles. So because they're not congruent circles and they have the same measure, these will not be congruent arcs. So not congruent, different circle sizes. I'll say not congruent circles. Not congruent arcs because not congruent circles with same measure. See, you can have, well, actually, I don't know if that's true because circles are similar. Yeah, as long as the circles aren't congruent, I think you're good in saying the arcs aren't congruent. They can have the same measure. It's possible. But that's all that. All right. Exercises 23 and 24, find the value of x. Then find the measure of the red arc. So this is an entire semicircle BCA, and I can add those two guys up, right? I'm just going to write this the first time. After that, I'm not going to do it anymore. Measure of arc BCA is equal to the measure of arc BC plus the measure of arc CA. So that 180 degrees of the semicircle is 2x minus 30 plus x. 2x plus x is 3x. If I add 30 to both sides, I get 210. If I divide both sides by 3, I get 70. It's not in, that's not a degree value, but that's x equals 70. Now, we need to find the measure of arc BC. Measure of arc BC is 2 times 7 minus 30. What? Oh, 70. 2 times 70 minus 30. I'm like, that's going to be negative. 2 times 70 minus 30, which is 140 minus 30, which is 110 degrees. That's where we have the measure of something in degrees on that. All right, number 24, let's do the same thing. This entire sum of all four of these unknowns will add to 360 degrees. So number 24, we can say 4x plus 6x plus 7x plus 7x equals 360. 10x, 24x equals 360. Divide both sides by 24. Is that 15? Yeah. X equals 15 in that case. We need to find the measure of that red arc. That red arc, we don't call it RT. We have to use RST. It's a major arc. It goes beyond that, 180. And this answer should be beyond 180. Maybe it's like 190. I don't know. Measure of arc RST is going to take 6 times 15 plus 7 times 15, which is 90 plus 105. Which is 205 degrees. 195 degrees. 195 degrees. Okay. All right. There's 23 and 24. Let's go to number 25, making an argument. Your friend claims that any two arcs with the same measure are similar. Your cousin claims any two arcs with the same measure are congruent. Who is correct? Explain. Oh, do one of them have to be correct? I don't like when my friends and cousins fight. On number 25, your friend is correct. We've already seen arcs with the same measure, but not congruent. Your friend is correct. Circles can be of different sizes, but are all similar. And when they possess same arc measures, those arcs will not be congruent, but also similar to each other. So cousin, not quite correct there. Now, if you have congruent arcs, then they're supposed to be, for circles, congruent arcs would have the same measure, but not necessarily the other way around, not the converse. Number 26, making another argument. Got a friend making more claims. This time your friend must be wrong, huh? Let's see. Your friend claims there's not enough information given to find the value of x. Is your friend correct? Explain your reasoning. Oh, friend is slipping. So what we have here, and I'm gonna find x for you. What we have here is an example like this one of a diameter. Therefore, this is an example of a semicircle. If this is a semicircle, its measure is 180 degrees. So I could take the x plus 4x, I'm going to solve it first and then dispute my friend, and I get 180 just from that off the bat. Combine like terms, divide by 5, you'll get the answer, if only I knew what that was. 36. X is 36 from that one. Your friend's incorrect. Look at the math. Your friend is incorrect. Why would your friend make such a ridiculous claim? Your friend is incorrect because semicircles exist in the diagram and thanks to the, I need a comma. And thanks to the arc addition postulate, I believe it's called, arc addition postulate, we can add the measures of the unknown angles, set them equal to 180 degrees, and solve. And solve. See above. All right. There's number 26. Friend was right, then friend went straight away and went wrong. Number 27, error analysis, as well as 28. Describe and correct the error in naming the red arc. I'm going to guess. I saw a major arc. I'm going to guess they're going to use 2 letters. So, number 27, I might be wrong. Number 27, they use 2 letters. All right. And correct the error. So, they used 2 letters to describe, to name a major arc when they needed to use 3. Remember, 2 letters is to describe a minor arc. So naming that arc correctly, let's correct the error. It starts on A, crosses through B, and hits D. Let's call it arc ABD or arc DBA. Let's just say both. Arc ABD or arc DBA. Those are the only 2 accepted answers for that. All right, number 28. I like to try and guess what it is before. Describe and correct the error in naming congruent arcs. Oh, I have no idea what they're going to say. Oh, I see. Okay. So JK is congruent to NP. So they're on some right track as far as central angles will have equal. Because they're vertical angles, these are congruent. And then because these are congruent, we're going to have equal measures here. If this was 30 degrees, then this is 30 degrees, and this is 30 degrees, and this is 30 degrees, and 30 degrees. They can all be the same degrees. Doesn't make them congruent. Congruent means equal in size and shape. So these two, if I did like tick marks, these two would be congruent together. These two would be congruent together, but not the other ones there. So they named two arcs of differently sized circles to be congruent, which is not the case even with the same measure. So I don't know how to correct it other than saying, let's make JK congruent to something else. So I can say that arc JK is congruent to arc QR. So part of that same circle. And we can say arc, let's say LM, is congruent to arc NP. So those are the two different ones that do work right there. One or the other, but not the way that they wrote it. All right, 10 more questions here. I'm scared that proofs are going to show up. Number 29, attending to precision. Two diameters of circle P are segments AB and CD. Find the measure of arc ACD and the measure of arc AC when measure of arc AD is 20 degrees. So I got to come up with a drawing with this thing, I guess. Let's plot a point, call it P, draw a circle around that point. Using SpongeBob's technique of making a circle. So through P, they're bringing up diameters. So for example, this can be a diameter right here, but I want to see how they're calling what's the minor arc and stuff like that. So they said AB, so cool. Now they're mentioning measure of arc AD is 20 degrees. So I have to make sure that I make something that kind of, looks like that. I'm going to do a second diameter pretty close to this thing so I can make the essence of kind of a 20 degree angle, which means I can make this guy here D, and then the other one is C. So here can be like a 20 degree part with that arc. I'll just put 20 degrees right here. That means this is also 20, by the way. What else do they tell us? Find the measure of arc ACD and measure of arc AC. Okay, so ACD I probably could have done on my own without the drawing, but I think it helps facilitate what's here. If AD is 20 degrees, ACD is everything that's not the 20 degrees. So measure of arc ACD is 360 minus 20, which is 340 degrees. And then they said measure of arc AC, this guy right here. We kind of saw the last question like this. Here's a semicircle, right, when it comes to diameter. There's a semicircle of 180 degrees. So measure of arc AC, we're going to take out the 20 degrees from there, and we get 160 degrees, like so. All right, those are the two. And yeah, the drawing, it did help. Even if it wasn't helping for me, hopefully it helped you teach in what we're doing. All right, 30, in reasoning. In circle R, looks like I have to make another drawing. In circle R, measure of arc AB is this, BC is that, CD is that, and DE is that. Find two possible measures of AE. Yeah, I think I do want to draw this. Let's check it out. What are they bringing up here? They don't really bring anything about the center. Oh, circle R. Okay, so circle R. Measure of arc AB is 60. I'm kind of like do it as to scale as I think I got. So there's a good old 60 degree guy. AB, 60 degrees. Remember, the arc and central angle are the same, so I'm going to put it there. BC is 25, so I'm going to continue down on this path, but not quite 90 degrees. Probably a little bit like that. So we'll say BC is 25 degrees, so this can be C. I think I made the 60 maybe just a hair too big. CD is 70 degrees, so here would be maybe like a right angle, so let's go a little less like that. So 70 degrees for CD, and then DE is 20 degrees. Okay, the only problem is I don't know if this makes a semicircle or not. 60, okay, I'm going to have to do some adding beforehand. So 60 plus 25 is 85, plus 70 is 155, plus 20 is 175. That's slightly less than 180, which means it's not quite a semicircle yet. It's going to look maybe like that. So we can say 20 degrees there from arc DE. Not quite the semicircle. They said find two possible measures of arc AE. Got it. Okay, here's the thing, right? The arcs didn't have to do what I did, but I'm going to provide one of them. This is considered a minor arc in this case, and I kind of said what some of the things are here. Measure of arc AE could be this where we go 60 plus 25 plus 70 plus 20, and I think I said that was 175 degrees. Now that's still a minor arc, so that still qualifies. The other way we can do this, and I don't know if it's going to seem weird, but you can go backwards in direction a little bit. Because I don't know how else they'd say that. This kind of becomes open-ended, but check this out. What if I said, instead of central angles, let's kind of just put them up. Well, I don't know where to put them. What if I put BC this way? What if the degrees were going this direction like that? And like C is right here. That doesn't take away from the fact it's a minor arc, and this is still a minor arc. So maybe we could do that where instead we're kind of subtracting the 20, and we still have a 70 degree thing from, say, C to D. You know, I did something like from C to D is still a 70 degree angle there, and then from D to E is still a 20 degree angle. So everything shrunk within, and there are a lot of ways you can do this. That's why I'm saying it's very open-ended. This would open up a plethora of different ways that you could make those happen. Whoops. So this time, right, from A to B, it's still 60 degrees there. From B to C, however, is the 25 degrees, but it goes backwards. So now we're doing like a 60 minus a 25 there, and the 70 degrees goes from C to D like that. This is 70, okay? And then there's the 20 degrees that I decided to put right there. So as a whole, I mean, what are we really adding there? I could say the measure of arc AE. This is a brand new arc. I don't know if this is what they mean, but that's kind of what I'm going to do. I can take the 20 degrees from this. Then why don't I just take this full 70 plus the full 70. Now, do I do the plus the full 60? No. I'm going to subtract 25 from 60 and whatever remains there. 60 minus 25 like that. And then I get 90 plus 35, which is 125 degrees. A brand new kind of minor arc from that thing there. Just a way different look. I don't know if that's what they mean. So let's find two possible measures of AE. I'm like, there's only one. But yeah, that's what I'm going to go with there. I don't know. That looks good. All right, number 31, modeling with mathematics. On a regulation dartboard, the outermost circle is divided into 20 congruent sections. I think they're talking about this part right here. What is the measure of each arc in the circle? Well, there are 20 congruent sections in that thing. I can do 360. They don't say explain, so I'm just going to calculate it. 360 divided by 20, which should be 18 degrees each per section. So 18 degree measures. That means the central angles here are 18 degrees. 18 and an 18 and an 18 and an 18 and all 20 of them added up. And I didn't know that there were 20 of them. Now I'll tell my brother-in-law that. All right, number 32. Modeling with mathematics. Okay. You can use the time zone wheel to find the time in different locations across the world. Okay, where's like Greenwich? Seriously, they don't have Greenwich for Greenwich Mean Time? Anyway. For example, to find the time in Tokyo when it's 4 p.m. in San Francisco, rotate the small wheel until 4 p.m. in San Francisco line up as shown. Oh, I see. The middle thing rotates. These things stay static. Okay. So okay, got it. That's cool. I want to buy one of these suddenly. Then look at Tokyo to see that it's 9 a.m. there. Okay, totally got it. All right. What is the arc measure between each time zone on the wheel? So how many time zones are there is the first question here for part A. I'm not going to draw the wheel, obviously. They go 12 to 12 and double. So 24. So I think we do 360 over 24. 15 degrees each, basically. Part B, what is the measure of the minor arc from the Tokyo zone to the Anchorage zone? I was going to say, do they want minor or major? But they said minor. I'm trying to find a good color that'll work. Let's bounce it off with some yellow here. Tokyo. Tokyo's here at the 9. And Anchorage is at the 3. Now, the thing to be careful of here is, I don't just want to do, maybe I do, 9 minus 3? Well, no, not quite. It's just the way that it counts it, but I'll still count it. 1, 2, 3, 4, 5, 6. Okay, 6 time zones of those degrees. So we're going to take the 6 that there are from one to the next and multiply by 15 to get the central angle and therefore that minor arc. So 6 times 15 is 90 degrees. It's a right angle, basically. Part C, if two locations differ by 180 degrees on the wheel, then it is 3 p.m. at one location when it is blank at the other location. So p.m., I guess it's the p.m. side right here. Let's just draw a diameter through there to the 3 a.m. Oh, duh. I guess I didn't need to say anything. There would be 3 a.m. on the other side. So 3 a.m. if they differ by 180 degrees. Was that it? Okay. I thought they were going to make us do things with the time zones. Seriously, why isn't Greenwich on there? Or which one would represent Greenwich? Helsinki. Where are we? San Francisco. I'm in San Francisco. I guess Belfast. Belfast would be the equivalent, I believe. All right, number 33. I think it said proving. Proving a theorem. Write a coordinate proof. Oh, I guess we can do that. Of the similar circles theorem. Circle O with center at 0, 0 and radius R. Circle A with center at A0 and radius S. Prove that... Let me lock these in place here. Give me 1 second. Sorry. Give me one moment here. We'll get rid of this. Lock that. Paste that back in. All right. Prove that circle O is similar to circle A. Let me just bring this over and see what the heck I can do with this. Okay. So number 33. First thing we want to do, it's kind of what we did before. I'm going to take circle A and I'm going to translate it over here. Now, I don't know if I'm supposed to type these things out or whatever and like redraw them, but step 1, I'm going to kind of make these steps. Step 1, we're going to translate circle A. A units to the left, right? This center is at A, 0. This is at the origin, 0, 0. Let's move it, translate it, A units to the left by going from some xy to some x minus A, y. Basically, everything is A units further over here. So now my circle A would look like this, and it's at 0, 0. I guess we call it A prime, right? That's what they say for those things. Now, one has a radius R, the other has a radius S. This one has a radius S on circle A. So I can kind of put that S right there compared to the R. So step 2, we will dilate. I mean, I'm not going to say these things right. I'm not very good at doing these. But dilate the points of circle A by scale factor of basically R over S. Whatever R divided by S is, let's say it's 2. It doesn't look like it, but let's say it was 2. If R divided by S was 2, then we're going to dilate it by a factor of 2. It's going to make it twice as big. I don't know if any of that kind of works, but they're similar. I don't know. Circle O, I'm not doing this right. Circle O is similar to circle A because I could apply similarity transformations. To map circle A onto circle O. I don't know. I'm not very good at that. Sorry if that's botched. I don't know if your teacher's giving you that question. All right, so that's as best as I'm going to do there. I'm giving up on that one. All right, number 34, abstract reasoning. Is there enough information to tell whether circle C is congruent to circle D? Explain your reasoning. Well, check this out. C's circle is right here, and a circle is defined as the points that are equidistant from the center. That means all these are the same distance away and all equal, and those are called the radius. That includes this one from C to that D. D also has the radius that goes right here as well. So they share the same, that segment congruent to itself, if you will, shares that same radius. So yeah, segment CD is congruent to itself. What I'm saying about that, let me actually say DC on the other one. So from center to edge and from center to edge by the reflexive property. I don't know if that kind of works there. So let's make this black. Therefore, what we're doing is concluding that these have this same radius. These each act as radii for their respective circles. And because the radii are congruent, this is the theorem, anyway, then the circles are congruent. So is there enough information? Yes. Yes, there is enough information. I know I ended with saying there's enough information, but I hope you understood why I said that. All right, number 35, proving a theorem. Use the diagram on page 584, I have no idea what that is, to prove each part of the biconditional in the congruent circles theorem. Let me pause and figure out what that diagram is, and I'll bring it over. Just give me, and I'll change this color to black, and then I'll see what the heck we're going to be doing there. I don't know if we're going to like use inductive reasoning or whatever. Just give me one moment. All right, so I found the one. This is the congruent circles theorem here. So what do I have to do? So part A, given AC is congruent to BD, prove it. I don't think they did two column proofs. What did they do? They just said because we translate it over and it maps onto that. So given the radii are congruent, prove the circles are congruent. So what I'll do is I'm not good at this part at all. It's weird that they're kind of making us do that. Translate circle A so that its center maps onto circle B's center. And what that will give us are, I don't know, congruent radii. I mean, the radii are congruent, right? Because the radii are congruent. Now, I can't say that there's the theorem, but because they're congruent, this maps the circles onto each other. This maps circle B onto circle A. Circle A onto circle B. What do they call it? I called it a similarity transformation before. This is a rigid transformation. A rigid transformation, such as translation. A rigid transformation mapped circle A onto circle B. Therefore, circle A is congruent to circle B. I don't know. I hope that's good. All right, so there's the first one, right? I don't even know if I need the diagram. I just wanted to use that. But here's the if and only if part, right? The biconditional. We started with this one and proving that. Now we're starting with this and we're going to prove that. So starting with circle A is congruent circle B, prove that these ones are the same. I feel like I'm going to say the same thing over again. Let me try and copy and paste this. I'm really, this is not what the solution guide's meant for on my end. So sorry if you're assigned these problems and going I'm very curious to hear what you have to say. Mr. Robinson's forte is not in this kind of proof, much less any other kind of proof. Okay, so translate circle. Well, let's see what I'm going to say here. Given that the circles are congruent, let's do that. Because the circle. Well, actually, I don't think we have to do a transformation here. Now that we know that circles are congruent, we just got to go by the definition and say that the points kind of work. So let's see. I'll say this. I'll say because circle A is congruent to circle B, the distance from the center of the circle to a point, the distance from the center of the circle to a point on the circle is the same for each circle, right? That's what radii are. That's the definition of a circle. That's how the thing works. So the radii are congruent. I'm just typing this instead of saying that segment AC is congruent to segment BD. I could say all that stuff. I just did, let me do it right here. The radii are congruent. Segment AC is congruent to segment BD, and here I'll say circle A is congruent to circle B. All right, there's the weakest proofs that I have there, but I hope that works. I hope I kind of did that right, but let's keep moving forward. 3 more questions. Number 36, and I see a proof down below. What's 38? Oh, this is not a proof. How do you see it? Are the circles on the target similar or congruent? Explain your reasoning. How do you see it? Generally seem to be very small problems. Well, the circles on the target are similar. They appear to be similar. The circles on the target are similar because they share the same center but have different radii. And are therefore not congruent. I mean, I guess when you're giving me an option of one or the other, if it's not congruent, then they're similar, and I think that's the way I'm just going to go about talking about it. All right, number 37, proving a theorem. Use the diagram to prove each part of the biconditional in the congruent central angles theorem. Okay, I don't think I needed to copy and paste the previous image thing that I had now that I understand what it is that we have here. So let's see what they're asking. Given that angle BAC is congruent to angle DAE, prove that arc BC is congruent to arc DE. Well, it's not congruent triangles in CPCTC that we do. What we can do is we can say that the measures are the same. Can we use the transitive property there? I think here we talk about them being in the same circle. So because there's that idea, I think the other theorem, I don't know if that was a theorem, but the idea that if you have two in the same circle and they have the same measure, then they're congruent to each other. So I don't know. Maybe we can say something like, given that those two are congruent, angle BAC is congruent to angle DAE, let's then say that measure of angle BAC is equal to the measure of angle DAE. That's kind of like definition of congruence still, even though it's like a different kind of way. Congruent arcs have equal measures. Equal measures doesn't necessarily mean congruent arcs, though, but if they're in the same circle, then it would. Now, the measure of arc BC, if you see right here, it's the same as the measure of angle BAC, right? I think that's the big thing, that we have to start with the congruent angles and go from there. Measure of arc BC equals the measure of angle BAC. That's, I don't know what theorem that's called, but that's the central angle theorem. And then the measure of arc DE is equal to the measure of angle DAE. So those two things are there. I don't know if we can say transitive property right there to say that those arcs are equal. I guess so. So measure of arc BC equals the measure of arc DE. Now, that's great, but they're congruent more so because they're in the same circle. Same circle. So arc BC is congruent to arc DE. And I think that's the final capper on that part because they're in the same circle. Or if they were in congruent circles. So if there's something else that we had there that would work that out. That's just part A. Oh, this is a biconditional statement. So part B, now we have to go the other way. We have to say now that we have the arcs that are equal, stuff like that. Okay. Let's go at it. We know that the measure of arc BC is equal to the measure of that angle, measure of angle BAC. We know that the measure of arc DE is equal to the measure of arc DAE. Now, whoops, I keep writing my E's as C's to begin with right there. Now, because we have that given, right? We have the given that the BC is, I'll make this its own sentence. Because arc BC is congruent to arc DE, then measure of arc BC, let's see, can I say that? Well, we know that those guys are equal right there, right, the congruent part, so I think you can go straight to that conclusion. Because the arcs are congruent, then their central angles are congruent, and because these things are there, I'm just going to go straight into that. I'm not really good at these proofs, I'm very sorry. It's not about congruent triangles. BAE, was it BAE or BAC? It was BAC is congruent to angle DAE. I think I'm missing some steps right there, just basically saying the transitive property stuff, but because the arcs are equal, because the measures are equal. Congruent arcs means congruent angle measures. That's kind of what I wanted to get into there. Okay, and the last question here is number 38, thought-provoking. Write a formula for the length of a circular arc. Justify your answer. This is tough for me because I already know what it is. So I'll talk about it. And you know what? I think it's good that I'm talking about. I wonder if that's what we're leading to next. I literally don't know what the next section is. But let's talk about this a little bit so we can get to that final thing. And I don't know which formula they'll eventually hang on. I'm not a fan of the formula itself because unless you understand why it is, which we can do together here, then it's nothing we necessarily want to do. So let's say that we're referring to some arc, and they never said the phrase intercepted arc yet, but let's say that we're referring to some arc that's right here. And I'll name this angle theta and this radius r. Now, the radius is important for this thing because they're talking about the length of a circular arc. The first thing you'd have to know is that, okay, the thing you'll have to understand about this is the length of this arc is whatever equal fraction that this arc's measure is out of 360 compared to the circle's circumference. Whatever piece this is, let's say it was a quarter of it. If this was a quarter of the circle, like 90 degrees, then we would take a quarter of its circumference. That's what we're doing. So we're setting up a proportion. So first we begin with the circumference of the circle is 2 pi r, 2 pi times your radius. That's important because we're going to set up a proportion here. Whatever this theta angle is out of 360, this, and they use the letter S, by the way, I believe, for arc length. It's not a 5. This arc length S is out of the circle's circumference, 2 pi r. This is the idea of the formula in a nutshell right there. How do you solve for S? You multiply both sides by 2 pi r. So S equals theta over 360 times 2 pi r. Now, there are other versions of this formula that are written. In other words, 2 over 360 can reduce to 180. You can put the pi and r on top if you'd like to. You can say S equals theta times pi times r over 180. I feel like they write it differently. They might write pi r theta. Theta pi r kind of suddenly looks weird, and I suddenly want to look it up online. But pi r theta over 180. And again, that's just because of how... I'm trying to think how they write it. I don't use it this way, but either that or that applies. I like setting up the proportion as far as giving you the logical idea. Whatever fraction this angle is out of 360, this arc length, your answer you're trying to find is out of the circumference of your circle. And that's how you find arc lengths, and that's something that we're going to get into later. So I'm only talking to a select few of you who would like to watch this video to the end, and congrats to those who did it. All right, guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. This is the end of section 10.2. On to section 10.3, probably finding the lengths of arc measures. I have no idea, but we're going to get into something pretty soon. Hey, take care. I will see you in the next one.